Is there any science or astronomy that can only be done from the surface of the moon? And if that is the case, how do we make sure that other interests, such as commercial interests or other national interests, don't supersede science? Who gets to decide that? What type of national or international bodies can take decisions to preserve science on the moon? Please join in this episode of Chai on the Moon, where we have this conversation with Professor Richard Green. Hello, and welcome to Chai on the Moon. This is where we talk about societal and ethical issues related to human settlements in space, in particular on the moon. Today, our guest is Dr. Richard Green. It is my honor and pleasure to have a conversation with Professor Green. He has had an illustrious career in astronomy, and I'm not going to list everything, but his research interests are in active galaxies and quasars. Uh, but he has served as director of, amongst other institutions, Kitt Peak National Observatory, which I had a chance to use a couple of telescopes actually for my PhD work as well. The UCURT Observatory, the Large Binocular Telescope, and he was also the division director in the Division of Astronomical Science at National Science Foundation. He was elected as a Legacy Fellow of the American Astronomical Society in 2020. But for our purposes, he is the chair of newly formed International Astronomical Union's Commission on Astronomy on the Moon. Professor Green, welcome.
Well, thank you, Salman. I'm delighted to be here and to talk about this great subject of mutual interest because the future is so exciting for what's happening there, and everybody wants some guides and rules for how we share that exciting opportunity.
Great. So let's jump right in. And so, for a lot of people who are going to be thinking about, and that is, well, what's so special about the moon regarding astronomy? I mean, we have the Earth, we do astronomy here. So, what can moon do for astronomy? What Earth cannot?
There are three or more ways of taking astronomical observations where the moon is the best place in the whole inner solar system to make these observations. So, since you asked, I'll launch off and describe each one of them a little bit and say why the moon is better than Earth and better than orbit. So, so the one that people know the best because the idea has been around the longest is studying the very early universe in low frequency radio waves. Um, the This is a time called the cosmic dark ages, before stars lit up and galaxies formed, when the universe was a soup of cold neutral gas. And neutral means that every atom had all its own electrons attached. And we have a theoretical notion of how gravity started to work on tiny fluctuations in that gas to make bigger and bigger structures. But it would be fascinating and really important to observe those directly. So the most common atom by far is hydrogen, and its strong signal is it cools itself by radiating in the radio at a wavelength of 21 centimeters at rest. But we're looking in the very distant universe where the expansion makes it so that that wavelength is very highly redshifted, which means it puts the signal down at very low radio frequencies of in the VHF range, in megahertz range for people who understand a little more about the radio engineering. And humans use that frequency range all the time on our planet. So it's our garage door opener, it's airplane transponders, it's my electric shaver being noisy. And so there are very few places on Earth where there is enough shielding from our artificial signals that allows you to put a radio telescope with enough sensitivity against the galaxy's own radiation in those frequencies and against our human made interference. Now, we're hopeful that the next generation of communication satellites is going to be relatively quiet. We understand that SpaceX was made aware that they were leaking radiation from their unshielded electronics, and their next generation of satellites is now more quiet. So, we hope that satellite operators are responsible. But nevertheless, the backside of the moon always faces away from the Earth, and therefore it's always shielded from that kind of radiation. And so it was recognized almost 50 years ago at the UN's organization that distributes radio frequencies that the backside of the moon should be protected for that kind of radio astronomy. So indeed, that's one of the most exciting problems that can be done. Secondly, um, we've been excited uh, for the last 5, 6, 7 years now about the detection of gravitational waves. It was so thrilling to see LIGO finally turn on with full sensitivity and see black holes merging. And then when it's in its next round in 2017, there was that neutron star merger that actually had an electromagnetic signal. And so we're learning about compact objects in the universe and getting all kinds of surprises, which is quite wonderful. Um, but the moon is a special place to make those observations because it is seismically a lot quieter than the Earth. So it can go down to lower frequency disturbances. And remember, they're measuring the stretching and shrinking of the moon with the passage of a gravitational wave that's a fraction of the diameter of a proton. So it's a very sensitive measure. But there are frequencies that are lower that can be detected from Earth platforms just because the Earth is always rattling itself from its activity. And there is a gravitational wave detection array of satellites that's intended to be launched called LISA. And that's going to be really wonderful for very low frequencies, but the moon captures the one in between the range in which the Earth is sensitive, which is stellar mass black holes largely, what LISA is sensitive, which is very massive black holes, and they can come right in between. The moon is also especially good for one way of detecting gravitational waves, in that the way LIGO works is to have a classic, what's called an interferometer, two beams of light that you recombine, and it measures if there's any change in the distance of the two mirrors at the ends of long tunnels. And those tunnels are pumped to a very high vacuum by Earth standards, but the surface of the moon already has a 10 times better vacuum than that. So
Hmm.
it's really a great place to set up that kind of measurement. Another completely different approach is to have an array of seismometers, basically, and they measure how the moon's shape is deflecting. Those need to be cryogenic, but the moon has craters that have been shielded for forever, essentially, so that it's cold, cold, cold on those crater floors, and you could use that to make such a measurement. The
If I
third
can,
kind, go ahead,
if I
please.
can ask you about a follow up to that, I mean, I mean, because you did mention for gravitational waves in particular that there are three different types of frequencies that you can get, and the moon can be good for one particular type of black holes, for example. Uh, but for radio telescopes, the ones that you mentioned before, there is no sort of like analog, or sort of like, space cannot work for that. Like, I mean, people would think, oh, so we put telescopes in space like James Webb or Hubble Space Telescope. So why? So would radio telescopes just be on the moon, or do you think that can also be in space, that can work somehow?
It's helpful, if not essential, to have a, a ground platform for telescopes of that form, because they're basically, it's almost like barbed wire. They're dipole, they're very simple dipole antennas that are connected one to another by a long wire, and then there needs to be a central processing station. And so you could deploy the middle term aspiration is to have an array that's about 10 miles wide, and ultimately almost 100 miles wide, of these long wires with these simple antennas. So just from a logistical point of view, having a simple vehicle with a big spool on it is a lot easier way to deploy that. And remember, the moon shields you from the Earth's radiation. There are not stationary spots in orbit in which that happens. So you're under the umbrella, so to speak, to do it on the moon as opposed to out in space where you can see the Earth.
And you had
So
the third thing. So there were
that's
two,
the
and then
third
you
thing,
said the
right?
third. I just wanted to get back to that.
No, that was very good. So the third thing is that there are these naturally cold traps on the moon that allow you to make um, a telescope that is naturally cooled. And once you have a very cold set of optics and structure, that allows you to make a very sensitive observation in the thermal infrared, where normally the components of the telescope themselves are radiating so strongly that it's very hard to measure things coming from the sky. And the Earth's atmosphere also blocks much of that radiation. So, at minimum, you have to get into orbit. But again, here's a place where you would like to have either a very large collecting area, which is hard to launch, whereas you can assemble it robotically, or with humans in place, or you can, to get the highest resolution, you can have a distributed array of telescopes and you combine their beams by that process of interferometry again and make it as if it were one giant telescope. So, two things you'd really like to do scientifically that's very hard to do anywhere else. One is that this might be the platform to study Earth like planets around other stars, because if you're near one of the moon's poles, it's you get to watch a star, a planet going all the way around in its orbit, and so you get very good coverage and you can see what the atmosphere of that planet is doing. And a lot of the molecules that give you the signatures of what's going on underneath that atmosphere and in that atmosphere are in the infrared, in a place where it's very difficult for us to observe from the ground. So James Webb's Space Telescope is showing us how exciting it is to work with a cooled telescope in space, but they have orbital constraints that a moon basing doesn't have. The other story is another way of looking at cosmology, the same kind of assembly of structures in the very early universe. This goes back even earlier, because um, the hot Big Bang radiation eventually was let loose from the atoms, the material, and so the energy was free, leaving the material behind. And that's called the cosmic microwave background. And that radiation has been free streaming since that moment in cosmic time. And it's almost all of it exactly the same temperature. And so that is a characteristic curve in physics called a black body curve. And today, the universe has expanded so much that it's a little under 3 degrees absolute, the temperature of those photons. But there may be very tiny variations in that temperature that will give tiny lumps and bumps on that very smooth black body curve. And that tells you everything about the seed perturbations in the material that have then grown to be the galaxies, the clusters, and the large scale structures that we see today. So, making a high precision measurement in the mid infrared of the shape of that cosmic microwave background radiation um, with wavelength and therefore with temperature unlocks secrets in precision cosmology that will really give us the clues about how our universe got going.
So so that's actually, I mean, these are obviously, I mean, it covers the entire range all the way from the universe to extrasolar planets to a certain degree, and of course, my bias, galaxies in between. Um, but these are the positive aspects to that. What kind of challenges you see? Because Moon is also an environment where, while on the one hand it has these positives to that, but you also have a particular type of regolith properties over there. There are temperature variations. Are those in some ways impediment to doing this kind of astronomy, or in general things that astronomers will have to really worry about?
That's a great question. And I'm sure that's true because the far side of the moon has a day-night cycle, just as the side we see. And so there has to be power storage that charges up while you have the 2 weeks of sunlight, and then has survival in the deep cold for a couple of weeks while things are in shadow. And so that's going science and the exciting developments from the commercial world and national space agencies are going to clearly have to work together because that requires a pretty sophisticated power infrastructure. And, and if we want a relatively quiet zone in that shielded zone, there may not be a lot of other activity going on. So, we're going to have to set up a power station for that remote radio observatory, remote by the standards of where everybody else is working on the moon. There are terrain challenges. If everyone is eyeing those deeply shadowed craters, um, but they have steep sides. If you wanted to, it's like the inverse problem of delivering a telescope to a mountaintop. Maybe we will have to figure out how to just make a light baffle on an easier terrain to build on. So there are truly practical implications about deployment, even in our you know half century aspirations for how to build the state of the art astronomical facilities there. I'll give another example from my expert friend Martin Elvis at the Center for Astrophysics, who's written extensively on these questions. Um, I talked about a vehicle to unspool the radio antenna, and ultimately we want a sort of 100-mile plane. Well, there are limits on the slope changes that any normal vehicle can traverse and do work like that. And so that ends up that there are only 2 or 3 places on the shielded zone of the moon with large flat enough plains without craters and mountains and really rugged terrain to allow you to make such a deployment of even a simple system. So we have lots to learn, and we'll clearly need to work closely with the other kinds of activities that are going on as people learn how to make survivable electronics, to have enough power to get to remote locations reliably, and so these are not trivial challenges. It's a very difficult environment.
So this brings me to a related question, because you mentioned, which also makes sense, that in some ways a lot of the development is expected to come from the commercial side, and this is something that is also going to lead to breakthroughs that are also important for astronomy, as you mentioned, for example, how to survive, how to have batteries that can survive the daylight cycle on the moon. But at the same time, you have particular concerns about it for astronomy. So, for example, if there is commercial activity and they have their satellites going around over there, or if they have work going on of construction of lunar bases, for example, which potentially would also be problem for astronomy. So, what kind of challenges do you see in terms of that this commercial stuff versus which is helpful for astronomers, but also might be an issue, might be a challenge?
That's really the most interesting policy challenge, because there are not a set of sort of detailed operating modes just yet. There are the Artemis agreements, the Artemis Accords, which are a series of bilateral agreements with the United States on how you might conduct business on the moon. But it's highly unlikely that Russia and China are going to sign those agreements, just for instance, and they are have very active lunar programs. So we will need to build an understanding, first how to communicate, and secondly how to operate in in the context of the Outer Space Treaty, where the Outer Space Treaty says that everyone has equal access to all places on the moon, and that's kind of inconsistent, right, with actual operation. So the Artemis Accords defined this concept of a safety zone, where you can say within this radius I am doing things that are likely to interfere with other people, and so you want to consider that as I start my mine or whatever it is that they're going to do. So people are thinking about it, but there is not a sort of worldwide agreement on how best to do that. Why is this relevant to science? Well, for astronomy in particular, um, what we talked about is that whatever those places are where we put these sensitive measuring instruments, they really are pretty incompatible with the other kind of routine activities that other groups will wish to do. The radio zone really can't have noisy truck engines working nearby. The um, gravitational wave detectors really wouldn't tolerate a takeoff and landing zone or a mine with blasting and pounding on the ground. It's fairly obvious on the one hand, but what's not obvious is how to get through international agreement that this should be a scientific preserve of some sort, and needs to be to do its mission of science, has to be free of the other kinds of interference that other activities would do. Let me also say a word on behalf of our colleagues at COSPAR, because they are representing the community that wants to study the moon for its own sake. And both the regolith on the surface and just below, and these frozen ices encode the history of the solar system for almost 4.5 billion years. So,
Yeah, and just for people who don't know what COSPAR is, COSPAR is the Commission for Space Research, right? I mean, that's
that's
an
correct.
international body regarding that.
That's right. Um, but has not had until recently, when we, the International Astronomical Union, have started interacting pretty directly with them. Their largest scientific community is the one that wants to study the moon itself. And so how can they say, can you leave this particularly valuable region untouched for a while so that we can go and sample those ices before human activity changes, the deposition of, kicks up regolith from takeoff and landing and distorts what's on the surface. That, you know, will we find evidence of complex molecules that were deposited by meteorites and comets? Will we find the history of what cosmic rays were that were bombarding this part of the solar system? There's a lot of historical information on the near surface of the moon. And so, how a similar process question, how do we get international agreement to say we'll leave this area alone for a while? The challenge and the interesting one is that we as scientists would like to think that our noble activity should take precedence over everything else that goes on there. But the international treaty language says, and the Antarctic Treaty was a model in the 1960s for what turned out to be the Outer Space Treaty. But there's a really important fundamental difference between the way they treat Antarctica in that treaty and the way they treat the moon. Antarctica was set up to be a scientific preserve. There was really no intention of having commercial activity there, or a long time human presence to learn how to live in Antarctica. It was really to be for scientific study. So therefore, it was much easier to define what a scientific preserve is that has international agreement. For the moon, there is definitely the intention of preserving the ability to conduct scientific investigations. That's specific language, but it's sort of on an equal footing with other kinds of human exploration and the new commercial interest in converting regolith to other things, to creating the moon as our spaceport to then launch off for other solar system exploration, to mine, well, to search for valuable other materials. They know the water ice will be valuable for producing fuel and supporting human activities. So science is one of many things that go on. And ultimately, there needs to be a way that all countries can agree. This is a science preserve. This is a mine. This is where the humans are going to set up their modules. And right now, there is no such process. And so it's an exciting time.
But by the way, I think I may have, when I talked to you first, I mentioned that, and it gives me almost sort of like, I don't know how I feel about it, that this water that collected on the moon over millions and billions of years over the period of time, and it contains these amazing uh, sort of like information about encoded about our solar system, and then people drink it, like, so I just feel like, I mean, it should, I mean, if there is something sort of like, to be considered as a holy water, I mean, I think that should be it, where you'd sort of like, maybe take a little bit of it. uh, so uh, so couple of things. I mean, I mean, there are a lot of questions that come to my mind, but first, just from the international perspective, because you mentioned Artemis Accord has certain things, and of course, we are in the U.S., so that comes in. I'm curious, because there have been Chinese missions, and Chinese missions have been scientific as well. I'm curious, are there plans for Chinese telescopes for astronomy? And if you guys have been also communicating with them, I mean, so this is one of the places where there could be commonality in terms of beyond just the base. Like, that, okay, here is the Artemis Alliance base, or here is the Chinese Russian, but here is the idea of astronomy as a more global, or in this particular case more universal, because if you include the moon in there as well. So are there any conversations with Chinese astronomers as well in terms of planning for astronomy on the moon?
So I've made a real effort through our IAU working group to reach out to all the countries that are actively interested. And on that working group, we have a very articulate and collaborative scientist who is the PI on an effort to look for some of that low frequency radio signal. So he's taking a different approach to start, in that he has a train of satellites that are going to work together um, to act as a radio array, and when they're around on the quiet side, they can get that signal. But ultimately everybody wants to end up on the surface. So um, so at the scientific level, the PIs are very forthcoming about talking to each other.
And he's
You
Chinese. This person is Chinese.
Yes, he's
The
at the
one is
Chinese
okay. I
National
see from the
Observatory.
Chinese.
Yeah, yeah, and he, at one point, his project was collaborative with Europeans. At the current time, I think they're in an intermediate stage where they're doing more studies. But um, you bring up an issue that the IAU is very interested in exploring, which is what is the ethical conduct of research on the moon, and how do we make doing astronomical research consistent with the Outer Space Treaty calls it non-appropriation. In other words, no one country can claim an exclusive access in that principle. So suppose we've figured out a way that the other thing that's interesting about the framework for thinking about how to do this science is it, it overwhelmingly likely will go through the United Nations committee that oversees it, has oversight over the Outer Space Treaty and how nations conduct themselves in outer space, and that's called the Commission on the Peaceful Uses of Outer Space. And historically, they have operated by unanimous consent, so that every single co-signer of the Outer Space Treaty, including Russia and China and Iran and all the European countries and the United States, all have to agree on a principle. And so it's not like a majority vote. So this is a slow and deliberative process by which full international agreement is reached. But that being said, what does it mean? Suppose that we have a process by which we can say we're reserving that crater to build a giant telescope. Then what does non-appropriation and ethical conduct of science actually mean? Does it mean that we devise some way that every country agrees is a fair competition, and project groups propose, and there's an international jury and they say, yes, we like this project the best? Or is it that one country can say, we're prepared to build this telescope, but the time on it will be completely open to astronomers' competitive access from any country? Or do you say that there are only a certain group of proposers, but the data immediately become public so that anybody can work on their exciting results? How do we, as observing astronomers, implement and telescope builders, how do we implement in practical fact an ethical and responsible way to make sure that all astronomers in the world uh, get what's promised in the spirit of the Outer Space Treaty?
That would be. I mean, that seems like. I mean, here also. I mean, obviously, you have directed telescopes, and so the challenges associated with that. But I mean, having that at an international level, I mean, I think that seems pretty daunting. Um, you mentioned Antarctic Treaty, and you also differentiated between how Antarctica sort of like ended up being more of a research base, and from what I know a bit about that, I mean, that was also a bit of a political issue because it was the US and the allied countries, and they wanted to keep the Soviet Union out. And so, in some ways, that's what it was. And it survived. I mean, so whatever the cause, it ended up being a research base. I mean, I'm curious. I mean, in some sense, the future of the moon hasn't been written yet. I mean, in the sense that what's going to take place. I mean, you mentioned the model where you can have these different zones. You have astronomy zone, or you have commercial zone, and you have others. Do you think there is there might be an appetite for at least the moon? Mars or other places or asteroids, that's a separate thing, but at least for the moon to have where science can take a bit more precedence than commercial activity, for example mining, because in some sense, as you had also laid out, I mean, in cases, for example, if people are digging stuff, or if there is landing and taking off going on, well, that challenges or that impacts gravitational waves, or with radio astronomy. Do you think, uh, not in a completely idealized world, but even more in a practical sense, that moon can become more or less for smaller settlements, for astronomy, and for maybe for launching services that can take people from there, but where the value that we put on the moon becomes more heavily in the direction of conducting science? Do you think it's a possibility, or do you think that that is we are too far along with other interests, are too far in, that that may not happen?
Okay, so whatever you're going to hear now is just personal opinion for sure.
Yes, yes, absolutely.
um,
Yeah.
um, my bet is that it would be easier to come to international agreement on how to conduct science than it is on some of the other
Right.
activities that you talked about. So that science may be able to get a running start. Um, on the other hand, um, if commercial interests see an opportunity for both um, innovation and creating technical interests by public-private partnerships. You know, NASA is doing a lot of contracting to small innovative companies to expand their presence on the moon very quickly. And since it's several countries' national goals to use the moon as the spaceport for further exploration, and therefore use of materials on the moon is a key part of that long-term goal, then I think that will have pretty high priority, and that's a harder issue to sort out. You know, my policy experts feel that if things ended up as carving out a Chinese zone, you
Yes.
saw my dog's tail wagging before. So, yeah, they're important parts of our discussions
That's right.
in home offices. Period. Um, if it ended up being this is China's zone of interest, and this is Russia's zone of interest, and this is the U.S.'s zone, then that really breaks the principle of the Outer Space Treaty. That that ends up saying that they could dance a little bit, but basically that violates the principle of non-appropriation, where every other nation should have free access to any part of the moon in principle. Now, if you create an international science preserve where every country together says they need to be free of interference in this zone because they have seismically sensitive equipment or whatever, that I think that's fundamentally different from saying this is where China wants to build its spaceport. Um, or this is where the U.S. wants to build its spaceport. And And so the only addition I made to that idea, so I think it will be easier to get science started. And on the other hand, there's a lot of programmatic pressure from national space agencies and their commercial interests to move forward on establishing human presence, on getting the infrastructure in place to create this spaceport. And that is more challenging from the international point of view because China and Russia and the United States and Europe all have these interests, and it's not clear that they're in a mood to make one international program. And so, again, um, how how they create modes of saying, I want to use this space, and how do you get international agreement, and how do you resolve disputes, is a set of policy and legal challenge within the framework of the Outer Space Treaty that will take some real thought. Right now, there is a legal subcommittee that operates within the Commission of Copolis, and they are dealing with the entire question of resources. You know, in with the Outer Space Treaty as the treaty framework, you know, how can one country mine regolith and turn it into structures? Is that, are they allowed to own and process any of that? What's the status of that material once you've used it? So they figured out how to do that for moon rocks, but that was, again, more for scientific use, and this is for programmatic use. And so there are these interesting and urgent challenges that serious policymakers need to work on. So in that context, we want to make sure that scientific investigations are genuinely protected as a priority use as well.
I mean, so if I can say, I mean, to me, it almost looks the opposite way, meaning to say that because these are real intractable issues, and it almost lead potentially to conflict as well, which of course on the US side there is space force, and of course on the Chinese side as well there is military involved and things like that, and those are foundational issues that if you have a base, as you mentioned, even though you cannot own the moon, but once you have it and you create a security zone, basically you are basically making the same argument that, well, this is something that is mine. And so, I mean, to me, the interesting thing that you've been saying is the science part. A, it is important for it to be shielded not just from interference from radio waves, but also from interference from politics. Because, in some sense, that also is, if you can create a sort of like a zone which is for science, then whatever uh, conflict or whatever other things are there, science can be done because it's a very unique place. But also, I can see that that could be an argument in some sense where astronomy actually resolves, or science resolves, the issue of how to think about the moon, and especially if it gets a little bit of prioritization. I mean, I'm thinking again from the Antarctica stuff, Antarctic Treaty, because it was a political stuff, but then because of those issues, it became a research place. I mean, I can almost see that astronomy, or science, I should say, per se, providing solutions to these intractable political issues regarding the moon.
That would be, I mean, that would be very good. And it because there's a stronger desire to cooperate internationally on these scientific issues, as opposed to the more tactical ones that will be more challenging. It's possible that scientific agreement will lead the way and will be, a model for how they might resolve other issues. On the other hand, there are some fundamental differences where, we can claim that the science is an international activity more readily than a U.S. base of U.S. astronauts could make that claim. And we are also in close collaboration and communication with the people who want to preserve cultural and historical sites. I mean, the first footprint on the moon is a place that was a landmark in the history of mankind and space exploration. And so there's a very active group called For All Moonkind that is working to preserve heritage sites. And again, that's that will come into the question of, well, that was the first U.S. footprint on the moon, say some other countries, and so how do we find a comprehensive list of historical sites? One thinking out loud approach that people are doing at the moment on the policy and legal side is to say, um, rather than saying this is going to be our observatory site forever, you say, this is, we will use this for a finite period. So that, and then if in the process the diamonds are discovered underneath the telescope, the miners can come in later and have a turn, so to speak. And that may be a very important approach for the people who wish to sample the ices and an undisturbed lunar surface, where they can say, we need 3 years of sampling, and then you can come in and make your mine, so that, if we can not make a permanent claim, but make, a scientific claim for use for a specific area, but for a limited time, maybe that can satisfy the sense of non-appropriation in the Outer Space Treaty.
So before we are coming down to it, and I know about your time as well. Uh, I'm just wondering when you mentioned uh, that are there, and I was thinking about sort of like some of the telescope controversies here on Earth as well. Are there concerns from the astronomy side of uh, telescopes being visible, for example, from the Earth? I know that the large 100-mile radio telescopes, that will be on the far side, but I don't think there will be any structures that might be visible. And I'm thinking in terms of for those groups who are pushing for, I mean, like, that, well, I mean, the moon is a heritage of humanity, and the way we look at it, it should not be deformed, for example, and those type of things. And that will be a separate issue in terms of human settlements as well. I mean, there will be lights at whatever, like, that we can see, or however it's going to be. But I'm just curious, is that something that astronomers are also thinking about, like in terms of, because bigger and bigger telescopes are possible, and so are there any such concerns in terms of what footmark they are leaving on the moon?
So I think it's fair to say that, that's a general cultural consideration, that, and astronomers, because of ground-based developments and because of their real sensitivities to, cultural concerns of indigenous peoples, who articulate that the most clearly. I think they the IAU would say that they need to be a voice at the table soon for any planning that goes on, so that all the concerns are heard and appropriately decided upon, but at least having them as part of the decision process.
And so finally, uh, but last thing is, what forum? So, I mean, obviously, International Astronomical Union is one place. Uh, which forum do you think is appropriate and potentially more effective in terms of dealing with the questions you are referring to? I mean, you also mentioned the Committee for the Peaceful Uses of Outer Space, but that works with unanimous decisions and things like that. So, do you think that is practical, or do you think it would be something outside of the United Nations that is needed, or you want to, or is it going to be within the United Nations that something is going to come up?
Well, I think it's important that all the scientific and preservation groups speak with one voice when they get to the United Nations.
Ah,
So each group needs to do its homework to say, what are our needs? What are acceptable policy solutions for us? Then all the non-governmental organizations talk together, which we do, to say, what's our approach to policy that benefits the, the broad sweep of scientific and non-space agency, non-commercial kind of activities that we want to see. But then it will be COPOLIS, it will be the United Nations, in which our voice needs to be heard along with the others. That, as I say, I think scientists can reach mutually acceptable conclusions more quickly and easily than these other competing claims. So I do need to leave you, but I do thank you for this great opportunity to discuss, and it's wonderful that you're bringing this to this interested audience.
thank you so much. Thank you for your time, and hopefully we'll be in touch, and we'll keep on getting other people to know about these issues that many people have not thought of.
Excellent.